A problem involving a very simple musical instrument. Now we've seen two different kinds of musical instruments, those that have waves on strings and those that have waves in pipes. And this is one that involves waves in pipes. This is a palm pipe. And I play the palm pipe this way. I take it, whack it against my palm, and I get a musical note out of that. That's why it's called a palm pipe. Hit it against my palm. Now notice this. When I hit it against my palm, it stays put, doesn't bounce off. Okay? That's going to be important for what we look at later. Different length tubes. Different notes. And so you can make a musical scale. If you want to do this, you have to compute how long do you want the tubes to make a standard musical scale. That's the problem we're going to consider today. Let's take a look. Here's our question. The palm pipe is a very simple musical instrument, a plastic tube played by hitting one end against the palm of the hand. If we wish to create a musical scale with these pipes, we need to cut them to the right lengths. How long should we make the tube for middle C at 262 Hertz? Well, there's one very obvious piece of information we need from this problem, and that's this, the frequency. If we're going to make a musical instrument, it has to be able to make different frequencies. In this case, 262 Hertz. But there's another piece of information we need as well. You play this tube by hitting one end against the palm of the hand. And that's important, and we'll see why when we start to solve the problem. Let's sketch a picture of what we have here. The palm pipe is a tube, and we're going to have a standing wave inside this tube. And to know the particular modes of the standing wave that we're looking at, we have to know what type of boundary conditions we have. Now think about it. You play the palm pipe by hitting your hand against one end. You leave your hand there. So here's the question for you. When you play the palm pipe, you put your hand against one end. What does that mean about the boundary conditions for this particular tube? We'll give you some choices. Given the way we play the palm pipe, that means this. We put our hand against one end, and so the tube is closed at that end. The tube is open at the other end. This is an open, closed tube. And what that means is this. We've been treating sound as a pressure wave. And if sound's a pressure wave, that means this end, the closed end, is going to be an antinode. The open end is going to be a node, because at the open end, the wave is up against the pressure of the atmosphere. It's not going to be able to change it. So the lowest order mode that we have looks like this. It's going to be a node at this end, the open end, an antinode at the closed end. Now let's look at the equation that we have for all the modes of a particular tube of this kind that is an open closed tube. The frequency of the mth mode is this. It's equal to m times v over 4 times L, where L is the length of the tube. The v in this equation is the speed of sound in air. We weren't told anything about the temperature in the room, but let's just assume it's a typical room temperature of about 20 degrees Celsius. In that case, the speed is 343 meters per second. But if we're going to solve this problem, there's another piece of information which we're going to need to consider. Remember, this equation gives us the frequency for the mth mode, okay? And m, the mode number, appears in this equation. If we want a frequency of 262 Hertz, which mode do we need to consider? Which harmonic sets that? Think about it. We'll give you some choices. Our equation for the frequencies of the different modes is this. The frequency of the mth mode is equal to m times v over 4 times L. For music, the frequency that sets the pitch, what your brain interprets as the pitch, is the lowest harmonic. Now remember, for an open-closed tube, the possible values of m are the odd harmonics. We have m is equal to 1, m is equal to 3, m is equal to 5, m is equal to 7, and so on. Those are our possible harmonics. But the one that fixes the pitch, the musical note, is the lowest harmonic. M is equal to 1. So that's the one that we need to consider. And so our equation just reduces to this. We're looking for the frequency of the first harmonic. That's just equal to v divided by 4L. Well, we know the frequency that we want. We're looking for the length. So we rewrite this equation like this. The length of the tube is equal to v divided by 4 times f. Now, we know the numbers for this because the speed of sound in air, we said we're going to assume, is 343 meters per second. And the frequency was 262 hertz. And remember, hertz we can also write as per second, so 1 per second here. And that's good because then the units are working out. The per second cancels, and we're left with meters. And if we calculate a number for this, here's what we get for the length. We get the length, 343, divided by 4 times 262 equals 0.33 meters. That's what we predict for the length of the pipe. Well, that's an easy thing to test, and let's do that next. So for middle C, the lowest note on the C scale, we came up with a length of about 33 centimeters, and in fact, that's about how long this tube is. As a matter of fact, when we built this set of tubes, we made that computation for every single one. We did the different frequencies for the different notes, calculated how long the tube had to be, and we made, with 8 tubes, a musical instrument on which you can play a song. That was the beginning of Bach's Minuet in G. It's a lot more fun if you have a lot more people to help out with it. Now I want to show you something too. This tube is a palm pipe, and when I play it, I hit it against my palm. It's got one closed end, one open end. This one is a commercially available tube called a boom whacker, and this one you play like so. Same pitch, bump, bump. Same pitch, twice as long. How come? Because this one is an open tube that I play this way. The palm pipe is an open-closed tube, different boundary conditions. And so it gives a different necessary length. Open-closed, open-open. Listen to the difference here. Open-open. Now if I close one end of the tube, I get a lower note. And that shows the influence of the boundary conditions. One of the important things we need to consider when we're doing calculations like this. But this is real. This is a real calculation, and the result that we ended up with was a real number, which really works. Not a huge surprise. Physics is about the world around us.